All right, well, hello everyone. Welcome to Computer Graphics again. Hope everybody had a good weekend. Hopefully the exam wasn't a big pain. But hopefully you got, I noticed there was a few common threads that I was seeing. So we'll probably address those a little bit today and next week. That way we just have all the understanding correct. All right. So I wanted to start out, now that the midterm is done, kind of look at where are we? All right. So, so these are the topics that we have talked about so far. Power of information, how really computer graphics is really centralized on how we display information to people and how we interact with that information. And it could be as simple as a video game where you're surrounding a system or environment around graphics and a person can interact with it. But the reality is some of the really powerful uses of computer graphics is just in displaying information or handling mouse clicks, all those like normal day-to-day things that allow us to navigate the web, use video, listen to music, audio. All those things are kind of lumped in there. So when we started out the class, we kind of like blasted you with a bunch of terminology. Here are things you may want to consider as you're doing your research projects. And then we spent some time doing game development because game development kind of introduces to the idea of systems thinking. In other words, you have a lot of moving pieces. How do you get them to work together? All right, so that's one of the reasons to study game development. And then we talked about mathematical foundations. So learning about vectors, matrices, quaternions, and so on. We're going to do some more with those as we continue studying. And then how do you use some of this stuff from a practical standpoint? So we looked at OpenGL, the pipeline, how models and vertices and all that flow through the system. How do you inject data in there in the form of textures? How do you process those with shaders? All right. And we see that you have a lot of moving pieces. They all have to be right or nothing works. And then we started to move into different ways of rendering. So we talked about the Reyes architecture, which is the classic rasterization approach, convert polygons to pixels. And then once you do that, then you figure out how do we want to shade them. So we spent some time talking about physically based rendering. So how do you get all of your vectors pointing in the right direction? We talked about the rendering equation. So what is the real problem that we're trying to solve? I put little asterisks there because those are topics that will be on the final since we weren't talking about those in the midterm. All right. So where are we going? That's a good question. And so coming up are the state-of-the-art presentations. And so this is your chance to kind of talk about the graphics problem you're working on and what you see as state-of-the-art for that. So that'll be next week. So we think we only have about 6 people participating, so we could probably do them in one class session. So do you guys have a preference for Monday or Wednesday? Next week. All right, we'll do it on, how about we do on Monday? Just get it over with. Yeah, Monday, okay. And we can just decide who goes first on that day. So I'll send out an announcement that the presentations are due. And so I think, and let me just double check the homework for, I have to go back. The homework is due on, well, I got to look at the project. So there's no homework this weekend.
The state of the art got moved this weekend.
I believe it is. So the state of the art's technically due, I guess, due on the 20th. Edit. My power to do that. I already got one in, so due on the 27th. Okay. And if you turned it in already, then you're ahead of the game. So there's no harm there for that. So you should be getting your bibliographies in there. Let me zoom this window real quick. Okay. So if you've never done who's never done a LaTeX bibliography or haven't done one up until this point? You've done one. Okay. So let's just take a few minutes to look at how that's done. It's pretty easy. So I'm going to go ahead and open up Overleaf real quick. This is just a quick side detour. Let's see here. Do I have the... So log in. Okay, so if you're doing your research, you're probably using some digital library of some kind, or you can use Google Scholar. That's another choice. In fact, I'll do Google Scholar. Why not? And let's just say you want to find Jim Blynn's wrinkled surface paper. There it is. And so this is on the ACM library, but there's a way to cite this. So if I click the double quotes here, there's an option for BibTeX. Okay. And so we click on BibTeX and you'll see we get this little text information over here. So we can just copy that. And I'm just going to create a new project, blank. All right, so once we have a blank article here, we can just add a new file and we'll call it research.bib. So .bib is the file extension for your bibliography, and we'll just copy paste our citation there. So then we need to add it to our paper. So at the very end, we can say bibliography, and we just type in the name of our file. So now if I want to go ahead and use this, I can say bump mapping was introduced by Blinn. And I can, we have this tilde here, which means it's a non-breaking space, so that'll keep your citation from jumping down to the next line. And then we use our command /cite. And so a good editor will automatically just tell you which ones are available. So we'll use Blinn 1978 simulation. And sometimes you get some tags. You can rename this to something easier if you don't want like a really big one. For example, if I was to go to the ACM and wrinkled surfaces, search the digital library there for this paper. If I were to look at the BibTeX, and some of these are going to be different depending on where you get it from. Click on this link. So while that's deciding to load, you can shorten these up if you want to, basically. So this is not any issue you have to worry about. So this is how you put the citation in, and then the bibliography, you can set the style. I like alpha. That's my preferred style. So I'll hit recompile, and you'll see that it goes ahead, and let me see if I can zoom in here. Oh, let me see here. Magnifier. There we go. Okay. Running a little slow. Probably because I'm sharing my screen here. But so you see over here, there's the citation. looks the way we want it to, and there's the in-place citation there. So I like to put the alpha because it lets me know the year and the author, and it makes it easier to find in a bibliography versus like 1, 2, 3, 4, 5. You know, you can kind of see if you got it right or not. Okay. All right. So that's how easy it is to do citations. This is extremely easy. And because it's all text-based, you can organize this however you want. And the cool thing about this, you can take this on to your next research project that you've already kind of collected articles when you want to do citation. Okay, so here's the ACM Digital Library version. If I hit BibTeX, you'll notice sometimes it'll give you this really long tag that's kind of, I don't know, it's a little unmanageable. I understand why they would want something that big because it's a computer system, but I'll sometimes shorten that, or sometimes I just don't care and I'll just use it anyways. But minimally speaking, you should at least have the author and the year. So, okay. Does BibTeX look easy to use?
Yes.
It's pretty easy. Once you get used to it, you're like, man, this is pretty great. If you've ever used Microsoft Word, that is also a pretty decent reference manager, but it's hard to get your stuff out. So it's kind of stored in an XML file somewhere, and XML is kind of ugly. And this is far easier to just type in something. So if you're using Google Scholar, this is a great way to just get that BibTeX out, and then you can just copy and paste it. And basically 2 lines of code at the end of your document will get you your bibliography. And if I'm correct, though, the report template for your project already has a bibliography. You just have to edit your stuff in there. So you can just copy paste and just start doing your citations right off the bat. Okay. And let's see if it's, yeah. And there are the citations right there. So this is formatted in the way that the ACM would expect the articles be formatted. So that's fine. All right. So that's pretty easy to do. And then you can see examples of how you cite a web page if you look in the references. Okay. All right. So let's go back here. So yeah, presentations are next week. And then we're going to continue talking about the OpenGL pipeline today. And then the coming weeks, we're going to start out by talking about ray tracing and global illumination, because we would like to write a ray tracer, all right, which is not very hard to do. This is where we go to the, we'll still be referring to the real-time rendering book, but this is a great time to start reading Peter Shirley's book. How many have started to read that already? Ray tracing in 1 weekend. This is, there's a, let's see here. They have a copy of it on the realtimerendering.com. And this is basically, you can write a C++ ray tracer. And by the end, following this tutorial, you can produce images that look like that, which is pretty good. Graphics, I think for a weekend's worth of work, it really is not bad to try this out. Okay. But it's nowadays, ray tracing is just one of those, I feel like one of those skills that will be in demand, people who can understand how it works. So you should definitely get to start reading that book. It's a pretty short read. It's not very big, and you can read it online for free. Now, I wanted to spend more time talking about edges and shading, so more NPR kind of stuff, and kind of get into texture mapping and procedural generation. So some of the more, I guess, useful techniques that you can use. So, and some of the, I guess they're the kind of graphics effects that you see in a video game nowadays, and you'd be like, it'd be nice to do that. So we'll spend doing that, and then we'll finish up by talking about lights and shadows and things. Okay, so midterm solutions. So let's go ahead and talk about, I still have to grade them. So I'm still working on catching up from being out of town. But close that. For the midterm, they're I'll just kind of go, the ones I feel like everybody has a good handle on, we'll just gloss over. If you have a question about that, then please feel free to ask the question. But as far as sampling goes, this is the, geared towards us thinking about, we have some kind of complex signal that either varies in time and or space. Okay, so an image is an example of a signal that varies in space, and audio might be an example of something that varies over time. Video is something that varies over both time and space. And so sampling essentially is how many do you take over a certain period of time, right? And that kind of has to do with, like how many times do you sample per second, or how many pixels do you measure, all right? And the components to that are bit depth. So we're trying to take an analog signal and turn it into a digital signal. So we need to turn it into a bunch of discrete samples. And bit depth will correspond to how accurate. So what's the range of values that we can collect on? The more range that you can collect on, the better you are able to represent, like, from a graphics point of view, sunlight versus indoor light. Okay. We talked about 0 to 255 is not a very good range of color, but if you can extend that bit depth, you can expand how much the lower and upper ranges are. And then sample rate corresponds to how accurate over time and space will your image or audio be. So one of the easiest ways to increase the quality of audio is simply double the sample rate. So if you were recording at 11 kilohertz, if you double that to 22 kilohertz or 44.1 kilohertz, suddenly you go from something that sounds very rough to something that sounds like you can't distinguish it from reality. Same thing with images. Most people have retina type displays on their phone. And so one of the easiest ways of improving image quality is just double the resolution or quadruple it, so that your eyes really don't see pixels anymore. They just see the edges. And then, and so that's one way you can do it. So the two ways that technology or displays are getting better essentially is, let's add more resolution, so that's sample rate, and let's add more bit depth, so that's what's the range of brightness that we can display on TV. Okay. And so the components for a data structure, we would need to a width and a height, and some array representing the pixels. So that's basically, I would think, minimum requirements to represent visual imagery. And you can start talking about, do you use a float? Do you use a byte? What's the, how do those correspond to bit depth and sample rate? Okay, photoreceptors, we got rods and cones. All right, so cones are good for color, rods are good for contrast. And then the tri-stimulus colors have to do with red, green, and blue. That's the ones we use in computer graphics. And then the violet question, right? Because violet's all the way on the other side of the EM spectrum. So the way that we perceive violet is basically because your red cones, we'll call them your red cones, are sensitive to that portion of the electromagnetic spectrum. So that is to say, if you were to take a bunch of people, line them up, and put them in front of a test that says, I'm going to show you a color of pure light. I want you to press the red, green, or blue button of the color you think that you see. And so if somebody were to actually see, violet light, typically they see, I don't know, probably about 2/3 of them will say blue, and about 1/3 of them will say red. And so that's how they measure your ability to perceive color. All right. And so this, you have to take into account people who have color blindness and so on. So they have different sensitivities. But if you're going to actually perceive violet, it'll look violet on your screen. And that's just because your cones that are responsible for red sensitivity are also sensitive to the upper EM spectrum. Okay, so that's how we perceive violet. All right, so I think everybody got this one right, but you probably read it from the book. I know there's a table. Okay, but not everybody took the coordinates and actually applied the formula for the shear matrix. And so that was part of the exercise. All right, so you should know how to apply a transformation matrix to a vertex in order to get the coordinates out. And so if you're trying to chase down a obscure bug, sometimes it does require you to kind of hand calculate, make sure that your matrix is doing what you think it should be doing. All right. Okay. Let's see here. Star Trek Wrath of Khan. Okay, so the 3 questions, we're testing a few different applications. So part 1, I was really testing to see whether or not you were going to use the cross product, because the cross product of 2 vectors is an orthogonal vector to the original 2. Okay, so if you're thinking right-hand rule or whatever the case is, maybe done this in physics, vector A, vector B, and vector C is sticking perpendicular, and that's how the cross product works. So anytime you need a orthogonal direction, like calculating the normal for a polygon, you can just use 2 edges, and those 2 edges make 2 vectors, and if you take the cross product of those 2 edges, then you get the normal, which is orthogonal to the flat plane of the system. So that is what we are trying to look for on number 1. Now, number 2, right? We want to find angle to fire the photon torpedoes. So we have 2 direction vectors and we have positions. And so we want to calculate theta, which is the angle between the Enterprise and Reliant. So the short way basically is we're testing our ability to use the dot product, because the dot product will give us the cosine of the angle. So if we want to actually calculate theta, then we can just take the arc cosine of the direction vectors for Enterprise and Reliant. The positions are important though, because if the Enterprise is pointed this way and it's at this position in space, and Reliant is over here and it's pointed in this position of space, you still need to figure out what direction, I guess, to send it to. So anyways, so if you know this angle, right, and you know this angle, then you take the vector between the 2, and then you calculate what theta should be. So you need to find a direction for, so really the direction for Reliant is kind of a red herring. You don't really need it. You just need to figure out this vector here, Enterprise and Reliant, so you can get the correct angle to shoot the torpedoes. Okay, now number 3, the Genesis wave. So we want to calculate a matrix for the ship to travel away. And so the 2 things we were testing here is whether you could construct a basis matrix. And we were learning that the basis matrix, basically the columns are the vectors. So the first 3 represents the x-axis, the second one is the y-axis, the third one is the z-axis, and then the last column is the translation. So where's the origin of the system? And so if we have the position of the Enterprise as P Enterprise, then you can construct the basis matrix by using those 4 vectors, okay? And then the second thing is to use a lookat matrix. And the idea here is that if we already know the matrix for the Enterprise, which we do because we have the vectors, UVW and the translation, and we multiply it by the inverse, what is the matrix times the inverse? Identity matrix, right? Okay, so once we have the identity matrix, then we really just need to get a lookat matrix, which this is the typical camera matrix where you start off, you got to give it a center point. So this is where the Enterprise is located. The lookat point is the direction we're trying to move away from. Okay, so if we're trying to find a direction away from the Reliant, right, at position P, well then the direction we should go is wherever we are minus them. That's the direction out of there. Okay, so so you can subtract. So So you have P enterprise, that would be the center, or yeah, the where the camera is located. So if you will, and then you have the target. So the center is where the enterprise is. The target is where you're trying to get to. And so it doesn't really matter how long that is. You just need to find a location of safety, right? And then the up matrix, or the up vector, then is just the orthogonal, which we found that out on the first problem. The orthogonal direction is up. All right. And that's pretty much what it is. So the basis matrix, just knowing how you use the basis matrix, and then 2, a lookat matrix, which is how do I make a matrix that just points to a position. Okay, so those are the 3 areas there. All right, and then a scene graph, right? We talked about a scene graph, and a directed acyclic graph just means it's the shape of a tree. All right. In other words, we don't have loops going back to other nodes. They all go one direction. And you could use a hierarchical model as a car, right? You might have the center of the car, and then you might have the body of the cars at the center. You have the doors, you could have the wheels, and those are all located relative to the center of the object. And then what happens in that case is then you could just move the top node of the car and everything else follows along. You don't have to manually move all the different pieces and calculate separate matrices. There's an automatic way of doing that. Okay, and so we wanted to modify this scene graph node in order so it could represent a hierarchical 3D scene graph. And so the easiest way to do that is just simply add a vector of children. And so if you have a vector of children, then now you can go down. So each of these nodes can then contain children, and then in turn they can contain children, and so on. So the only thing missing from this structure here is the children part. That's pretty much it. Okay. Rhea's architecture. So this is just a description of micropolygons and so on. And then these filtering terms have to do with what happens when you try and stretch a texture across a triangle or something. Is it going to look pixelated? Is it going to look blurry? What happens if it moves far away and we start getting all these like sparkly artifacts? So how do we apply MIP mapping, and what's the effect of doing bilinear filtering so we get those bands where we can see the transition from level to level? Trilinear will blend those together, but it tends to look blurry. And then anisotropic filtering tries to use the best sample. Okay, we tend to get very clear results with anisotropic filtering. And then lastly, organizing the pipeline. So we will start off with, frame buffer is last. Per fragment operations is next to last. So we'll start off with the vertex data. Well, it might be primitive assembly first. So vertex data, vertex shader, primitive assembly, rasterization, fragment shader, per fragment operations, and then the frame buffer. Okay? And so those are the references there. All right, any questions on the midterm? All right, the item that I think is the most important one to really internalize is the dot product and cross product, what you can do with those. It's probably, on this exam, easily the most important thing to understand. So it's because it's, those particular tools will enable you to kind of solve all the other problems, So whether it's lighting, whether it's positioning things in the world, how do you move things in the world? And, sometimes, and this applies to other fields, like if it's artificial intelligence, knowing, say, where the robot is located in relationship to the other objects will keep your robot from bumping into them, for instance. Or it could be useful in problem solving. So how do I get a robot to go from A to Z, navigating obstacles and so on. So those are vectors and these rotation, all these matrices are important tools that you can use to solve all sorts of geometrical problems. All right. So if there are no questions, let's take a look at per sample operations. All right. So, the questions for Monday. All right. So the first one, and we can just spend some time discussing these, right? So the first one is, why is reflectance a hard problem to solve in real time? So let's just go around the room and kind of gauge your idea for that. Why is reflectance a hard problem to solve in real time? I guess we could start with Levi.
It is complex and can have feedback loops going into it a lot, unless you can figure out a model to simplify it.
Feedback loops. That's interesting.
Like if you were to ray trace it, you could have things compounding onto each other.
Okay, so yeah, what amount of recursion, right? So recursion is kind of the idea there. So yeah, you have recursion is an issue, and especially in ray tracing. What about for real-time rendering? Like when we say real-time rendering, oftentimes we start talking about the rasterization approach. What do you think about that?
It's difficult to get right.
Okay.
You're not doing, you're trying to emulate what physics is doing with a different system.
So you get, okay, so like approximation issues, you can't sample all the paths. All right, next. Let's go next. All right. Daniel, right? Chris, sorry, Daniel. Okay, getting the names backwards. Okay, what do you think, Chris?
Well, one thing that he was talking about in the video is there's so many different aspects to the game. So he was showing that, like, you know, if you're high up, you have to make shadows look realistic, but also if you're sitting with someone, you know, light and shadows have to look realistic depending on like the clothing you're wearing, or if you're looking at a tree or skin. I don't know if that's the question you're asking.
Yeah, well, why is reflectance a hard problem to solve? I think it's a little bit more of the second question. Like, how do you prioritize? Well, kind of. It kind of goes along. Shadows, though, is a big thing. So you have levels of scale, right? It's got to look good from far away as it does close up. That can be a hard time for reflectance. I could see that being a hard issue there, just simply because do you arbitrarily, even at the close angles, allow super long light paths? Like, are you evaluating those, or you know, where do you say what's too short or what's too long of a light path to evaluate? Yeah. What do you think, Daniel?
Not sure. I wasn't really paying attention very much.
What do you think?
I would say it's hard to get accurate data depending on what model you decide to use.
Okay.
If you just have a surface that's flat surfaces, you're going to have a hard time getting a good reflectance from that. If you're using something that uses scattering, you might actually get something that has more accurate reflectance.
Okay. So yeah, I guess not using the right amount of geometric complexity and not using the right model can hurt. So if you only use diffuse, then you're always going to be, say, limited to, you're basically saying everything's like flat, it just reflects light. And so there's going to be limitations. You won't be able to reproduce certain kinds of phenomenon with that. Okay. Any more thoughts on reflectance? Maybe from a personal perspective, like how have you had to deal with this in the class so far? Or has it been like an item you shoved to the product backlog? Why do you think that is? Why does it get shoved to the backlog?
It seems like it's easier to just put something that reflects light. How do I say it? It's easier to create something that emits a color than it does emit a reflection. Definitely, you have to take into consideration the light, the angle, and how it reflects back into the view. You don't have to worry about microsurfaces, you don't have to worry about facets, you don't have to worry about scattering. It's just source to viewer. Relatively simple.
So I hear what you're saying there, and I'm wondering if you're thinking, when you hear reflectance, what are you thinking about? Like, what comes to mind? Reflectance. BRDF. That's new though, because you didn't know that before the class. Now you can't help but think BRDF. Okay. Okay, so you're thinking, okay, reflectance, BRDF. That's
Yes.
What?
Before that would have been the properties of the material. So like what percentage of light is reflected, what percentage of it scatters, what percentage is refracted, what like the dynamics of the impact.
okay. What do you think, Daniel? When you hear reflectance, what do you think about?
The way like a reflective surface portrays something that's on the opposite side.
Like a reflection? Is that okay? So there's reflection, which is a little bit different than reflectance. That's what I was thinking. I was hearing maybe from your answer. What do you think? Reflectance. When you hear that, what do you think about?
How well it can reflect whatever it is observed.
Right. So like you look at a shiny chrome wheel, it reflects the environment around it, right?
Versus that really kind of rock, it's not reflecting anything.
Right. Okay. And Chris, what do you think?
I think I took modern physics. I think back to that out of that class is reflection and refraction.
Yeah.
That's all I have behind it.
Yeah.
I guess that's what I thought of before in this class.
Okay. So, yeah, so that's actually, it's really important to understand what the problem is, right? So when you hear reflectance, we have to kind of change our mindset a little bit, because sometimes we just quickly think about a mirror. Like what am I seeing reflected off of a mirror? But in reality, reflectance affects everything. So even if an object looks completely dull like a rock, it is still reflecting light because you can see it. So the quality of how that rock looks then is dependent on what physics we use to model how light is reflected off of it. So just because it's not a mirror shiny ball doesn't mean that it's not reflecting light. And so that's one thing you have to kind of think about. And it's one of the things we've been thinking about for the physically based rendering is we could approach it from the standpoint of everything is like a mirror reflector or a purely diffuse reflector. But when in reality, what happens when we do that is that everything looks like 1970s graphics, or like ray traced 1980, graphics. Everything's shiny. It just doesn't look, or the edges just kind of have this fast fall off that we don't expect to see in real life, because you look around this room and you see very little, there's very little edges that suddenly just go dark on you. There's always some amount of reflection, that you see even on the edges. So we're always trying to figure out why is that? Okay, so whether we use something like Orin Air or the Disney one, that perception there of reflectance is going to solve a problem for us. And namely, that's where is all the light going? So if you only do like pure reflection or pure diffuse reflection, then you have a loss of light. And that corresponds to why the images don't look quite as good. But yeah, so reflectance though, it's a hard problem to solve in real time because it's the multiplicity of all the light paths that you have to consider. It's easy to pick a few, like, oh, I put a light in the room. Okay, that's fine. Are you also considering the lights outside the room? Are you considering the amount of scattering you get as light reflects on different surfaces before it gets to your eye? And so that's why it's a really hard problem to solve in real time, because you're trying to find out where is the biggest loss of light that I'm seeing, right? And you want to prioritize, and because and it also has to do with the kinds of materials you're using as well. So let's look at the second question, right? How and why would you prioritize one type of graphics problem over another?
To get a different visual aesthetic out of the product.
Okay, a different visual aesthetic. All right.
I mean, you have limited resources, so like, you can only use as many of them as you can to achieve whatever frame rate you're trying to go for.
Okay, so you might have a budget,
Yes.
compute budget, time budget, something like that. All right. What do you think, Chris?
I guess, like what I said the first time, if you're playing a game where you're up there like in an airplane, you don't really need to see the scattering. Like, what's it called when you can see the light scattering through someone's skin?
Like subsurface scattering.
Subsurface. Like, you don't need to see that stuff. Why not?
Mm-hmm.
So your computer doesn't need to be doing all this computation. It's unnecessary. So you wouldn't prioritize that.
That makes sense. What do you think?
I guess my question is prioritize for what?
Well, it's kind of, well, what kinds of things? I guess what is the what?
What's the goal of what we're trying to prioritize? If we're trying to go for realism, we want to prioritize more of the heavy features first. It's like trying to get specular multi-surface scattering instead of trying to make sure certain things are trying to reflect the color light.
Okay.
Versus something with cell shaded, you're probably not going to care about multi-surface scattering.
All right. So, okay. So one way to prioritize is like, do you even need it? Right. So look at what you're trying to simulate and decide, does it add to the visual realism or to the aesthetic realism that you're trying to portray? Okay. What do you think, Daniel? How and why would you prioritize one type of graphics problem over another?
It kind of depends on like what your end goal is. So if like, say you're trying to make a kind of like open world game or something, you would probably want to prioritize long distance rendering over some other things. Like usually when you're playing an open world, you want to be able to like see far out because it makes it more immersive. So I guess it just depends on what your end goal is. Also, whether or not you actually need any graphics problems for that end goal.
So what do you think of the, because I know that for their particular, when he was getting kind of towards the end of the talk, he was talking about, we haven't even begun to kind of touch this aspect and this aspect. Why do you think that maybe they haven't focused on those areas? Like hair rendering, for example, was one that he was talking about.
It's still cheap technically. It's still making it work.
Okay, so some things we can get away with a less than ideal situation because at the moment, right, it doesn't, maybe there's not enough bang for the buck. Like if I spend all my time working on better hair, but then the rest of the, you know, the items that you see that are taking more pixels at a time don't look very good, then maybe your priorities misplaced. What other areas maybe?
Well, they specifically were looking for like industry wins and technologies and characteristics that they can put in that make their product unique.
Yeah,
So,
kind of should their priorities, I guess, I mean, they're obviously going for an industry like lead industry, right? I like what you said there. But But what do you think about how should like those big wins then affect everybody else? Like if Far Cry is pushing the envelope in these certain areas, how do you think that affects other developers? They're going to want to know how to do that. Yeah.
Just have the understanding of how it works to be able to themselves.
That's okay. I like that. What do you think, Chris?
Well, I think that people playing their games would expect that from other companies. They see one company do it and it works well. And so the companies kind of have to catch up.
Yeah. What do you think, Daniel?
They probably want to implement their own like version of it, but like their own towards it, because they don't want it to look like it's just a.
Yeah, that can be hard though. Like, and this is, it kind of goes along with a conversation about, you know, what do you prioritize? Because if you're like going for a certain aesthetic look or something, sometimes those are a matter of like, yeah, our game looks like this, that's our style, right? But then there's like, well, we're using physically based rendering. So, you know, I would expect that I'm just, the physics, you know, it's not like I get to choose whatever physics formulas I want. You can't just make those up. They, you know, they are what they are. So, I guess my view on it is, you know, yeah, we should definitely be pushing the envelope, but it does, you know, if you didn't get this from watching this presentation, the what I like to call cost of entry is pretty high because you know, you throw all the formulas that he put up on the screen, and you're like, what? You know, and it does take some time, you know. Chris probably had a little bit better time seeing these formulas. Like, okay, yeah, I've taken modern physics. I've been exposed to like some of the depth there to some degree. Maybe not those formulas because we spend a lot of time. There's like, you get used to seeing BRDF stuff. And so for me, it's like, okay, I know what they're doing there. I mean, I have to sit down with a cup of coffee sometimes and like work my way through it. But they're, you know, the cost of entry, you go watch a presentation like that, and I would say most of the developers in the room would have some difficulty just working on that. And so, and some of those mathematical difficulties are things that you have to kind of prioritize as well, because you might have, you know, like the rendering equation still doesn't have a generalized solution to it. It's just a way of representing the problem. And that's why it's so important. But actually getting results for the problem, that's a different story. So let's go to this next one. 3 takeaways that you will use in your graphics future. So what I liked about that presentation is you could watch it, and especially since you're kind of new to graphics, you probably saw some things in there that you're like, oh, that looks like a good idea, right? So 3 takeaways that you think you'd probably use in your graphics future. So just hypothetically say that next semester you get a graphics job. So that's not, you know, 100% realistic because those jobs are hard to get, you know, just like game stuff or whatever. But let's just hypothetically say, you know, you're like in charge of a company that does graphics. What would you take away from that presentation? What do you think, Curtis?
Watch 20 minutes of it, not sure.
I think the main thing that I would go for was the process that he laid out for how to derive a new addition to the system, where he had a theory from somebody else or from his own, and then he would go through the process of characterizing it with, he said, what was it, Mathematica? Mm-hmm. And generating some lookup tables and some fields and stuff like that, and then building it into an implementation and testing implementation on that iterative process of building a thing within the context of graphics.
Yeah, that's. I think that's a good one. Yeah. What else? So yeah, testing. I guess taking theory, working on it with some math software, um, and then building your own experiment and then integrating it with the test case, I guess. So okay, yeah. So that's good. What do you think? We'll go with Daniel this time. Uh huh. Okay, we'll go with Chris. Chris's time.
On a lot of the videos, I think above my level, but I think it was really eye-opening. If he was talking about the process of how he came up with formulas, lookup tables, and also how he's making this product for like our team and all of the complaints that they've had with what I was doing. I thought was really interesting. And he's struggling to like please them because none of this is easy.
Mm-hmm.
And they want things a specific way. So just trying to compromise with them.
That's the team interplay. The artists want XYZ feature, and you're like, okay, you want, and they're going to tell you things like, I want the metal to look more realistic, and you're like, what does that mean? And so I really like the photo of like the car, for instance, kind of showing, can we get it to look like that? And being able to interpret, an artist's intent, because they have a vision of what they'd like to present a player, or, meet the goals for that particular 3D engine or for the product they're generating, so the interpretation there. What else? Other takeaways?
For new ideas.
Looking for new ideas in old papers. I really like that one. That's a really good insight there, because the more you study this, and this goes with anything, right? It could be as simple as how you rake leaves in your yard. Your dad may have like taught you, here's how you rake leaves and put it in a bag, and then you do it a few times, and then after a while you're out from that wing of like instruction you're doing on your own, and then you kind of go back and then you notice something else that he did that you're like, oh, if I add that, I'll get done, way faster. Or you start to learn some of the nuances that kind of go back in there, like that are in there. I guess they're deep in there, but they're hard to get out. They're hard to get out, and sometimes you don't even know what you have until you've had time to play with it, right? So sometimes when you look at mathematical equations, one thing I find fascinating is the history of these things. So like Euler's equation, right? I theta equals cosine theta plus I sine theta. And you're like, oh, okay, Euler did that. But you go look and, well, technically Euler didn't come up with that whole idea on his own. It had already come up. In fact, there was a young guy. He died when he was 33, but he worked for Isaac Newton. And he actually originally came up with the formula. But he died because of some fever. And so maybe he wasn't able to like dig out some of the elements there, but Euler was able to take that. And it's kind of funny how Euler gets attached to it. And then we sometimes think, oh, well, such and such person didn't understand it. And so you kind of go back and you look and you read and you're like, oh, this is interesting. So you look at some of these folks like Euler, he might have gone back and be like, this is what this means. This is why this is important. And so when you're able to kind of go back and dig into a topic and understand why it's working, and you can come up with new insights. That's why it's important to read the old papers, because we sometimes forget the thought process there. We kind of looked at that in the Power of Information lecture, where we were kind of looking at some of the old ideas that were before the internet or before modern GUIs. And sometimes it's too easy to be like, only look at new research, but then you forget all of the different concepts that were back there. One of the takeaways that I really appreciated was how they presented information. So I really liked how all the spheres are lined up, and they can kind of show, the material properties. And so at a glance, you can kind of see, well, what are the results of your research? And you can kind of see, oh, there it is. I can just see it. So I'm like, okay, so when I'm doing my graphics research, maybe I should take some time to focus on presentation. So what's going to enable me to debug this more easily? So that was one takeaway I got from it. I also took away the artist perspective, um, on a deeper level too. I also appreciated how difficult it is to touch modern software. So when this guy's working, I guarantee you that he is not checking in his code on the mainline branch. Otherwise he checks in the wrong BRDF and suddenly Far Cry looks terrible, and so I really appreciate the fact that, on the research side, they're almost, always kind of working along the next generation, but at the same time, you can't mess up a few of the takeaways I kind of got from there. Throat's dry. Okay. Yeah, the spheres, I thought the spheres were pretty good. There are other objects you can use in addition to spheres.
I found the cloth ones in particular because it's like, oh, that's a sphere of cloth. How interesting.
Yeah.
Perfectly isometric cloth.
kind of wrapped up. Yeah. So yeah, so those are, there's a lot to learn from the video. So if you haven't watched the entire video, go back and watch the parts that you didn't get. And some of this you really do learn by osmosis. You just kind of like don't get it the first time around, but then the second time around, or you go work on the problem on your own for a little bit. Like say, it's like, okay, maybe I should go implement GGX, or like we were in class, we were trying to figure out, okay, what are all the vectors that we need to have in place, and all those things will at least get you a step closer to understanding maybe some of the problems that are kind of being worked on right now, So then that's one of the reasons why I kind of picked an advanced BRDF like GGX to kind of start talking about, because, somebody here earlier was talking about, one person starts using it, the next person has to use it, right? And that's kind of what happened with different console hardware too, like PlayStation 4, for instance. So PlayStation 3 was kind of a, let's start using Cook Torrents model on everything. And Cook Torrents is pretty decent. That used to be like the de facto standard. And now that you're talking PS4 and Xbox One, everybody's using GGX, right? And that's just because the new hardware can support that kind of calculation. Sometimes you're limited by what the hardware can do, but as you get advances, the next the next hardware push next year, is going to be real-time ray tracing. You're going to, and it's not real-time ray tracing in the sense that the whole image is like pure ray traced, but from the standpoint of, yeah, we're going to start ray tracing ambient occlusion and all this other stuff that you might need just a sample or two per pixel, or better reflections, especially the kind of reflections that are not mirror-shaped ones. They're kind of rough. But that's like the next 4 years of development coming up. 4 or 5 years of development is everybody's going to need to be familiar with ray tracing and just, if you're going to work on, say, a AAA title, but even more so if you're going to be working on a PC where you have access to the kind of hardware that's coming out, already is out, I should say. All right.
A lot of that is also coming down to the noising
Oh yeah, denoising. Yeah, that's big push for denoising. Another fun problem I saw was clouds. How can you predict?
Clouds are noise.
Clouds are very noisy. But how do you, if Disney wants to like put clouds in the sky, how are they going to know they look good? And that's funny because artists are always trying to manipulate reality. They won't go for any old random cloud. They just want a cloud that looks good for that shot. So they'll tweak it, but they want to make sure that before they spend the hour rendering that image, that it's actually going to look decent when they actually send it off for production. And so those are. I just saw Toy Story 4, and the clouds shot at the beginning looked pretty decent. And I was like, okay, I know they're doing work. I know they're doing work on clouds because they were talking about that at SIGGRAPH last year. They actually have some cloud data you can download and try working with it. So yeah, clouds, path tracing, all that kind of stuff is.
And then one other thing, the first Q&A person, I couldn't tell because the image was tiny, but he sounded like he had your voice.
It was me.
Okay.
Yes, I did ask the question. Yeah, so I was asking about the wrapped cosine that they were doing, and because you can take a cosine, right? It varies from -1 to 1, but you add 1, and you can go from 0 to 2, and so the idea there is that you can represent reflection above and below. So that's their method of simulating subsurface scattering. So that was kind of interesting. I was like, oh, that's fascinating. And I haven't actually had time to check that out, but I'm going to do it right now. Wrapped cosine. Do this one. Let's see if we can't do. We have n.l, so we're just going to see what happens if you were to just do 1 plus n.l. Well, we'll divide it by 2, so it'd be 0.5 plus 0.5 times n.l, and just see what happens to the reflectance on there. Okay, so allow access. Oh. Why? I don't want that one. Okay. When things change on you. PowerShell. Okay, I could go for that. So this is also another good reason just to have a good, if you want to work on this stuff, just having a good like base code setup. Whether that's how to use this stuff in Unity or Unreal, that you can kind of experiment with these different techniques. So I'm going to go down here to I'll just do the NPR one. And I'm going to just take over, hijack one that I've been working on. So the hatch one is not, it's not even accurate right now, but we can do this. We can say return 0.5 times the dot product at n and l, because we know that it's going to return, we're going to get negative numbers as soon as we start going below the hemisphere. So this is wrapped cosine. So let's check out wrapped cosine. Oh, we broke something. Oh, it's got to be a vec3. Vec3. Okay. So this is technically wrapped cosine. Got to see if it looks correct or not. Oh, we need to add 0.5. So we just made it look dark. Okay. There we go. So this is wrapped cosine. So this is assuming that these objects are not really, let me zoom in here. So using wrapped cosine, is assuming that these objects are not, they're kind of translucent in the way that your skin is. And so this is the technique that they use to more or less say, this is what your, I guess, shading ought to look like. So if we were to put the sun elevation down, we need to use the the light, the amount of light, which is going to be Li. Okay, so the amount of light intensity. Okay, so we throw in this one, increase our zoom. So if we were to okay, so that's like the basis behind doing subsurface scattering in real time, is this wrapped cosine. Okay. This is definitely going to be a little bit more, I guess, harder to do, or harder to understand, because not a lot, when you start talking about this, people start getting very confused about what happens. And that's partially because the scattering is more difficult to kind of describe mathematically. Okay, so that's kind of what we're hoping to get. So some of this is use depth maps. So you kind of like figure out how much depth are you getting. And so they'll basically say, okay, what's the difference? So if I rendered this object from here to here, what's my min and max range? And simulating it in texture space. All right. Wrap shading. Let's see here if they have a better. Peter Pike Sloan. Well, I know who that guy is. He works. Oh, is he at Disney now, or is this older work? There's your wrap shading. So you allow the light to wrap around the edge of the horizon instead of just cutting it off. So it makes it look like it's partially backlit. So this is a cheap approximation to subsurface scattering. So another one is to use the cosine theta, so that's your dot product, n dot L, plus W divided by 1 plus W. And I wonder if they mention, is that, so this is no wrap shading with A equals 0.5 and A equal 1.0. So it's definitely a way of brightening up everything in the scene by doing it this way. All right, and there's looks like a sphere. So if you use a sphere, GPU gems, and so this is, if you're sometimes modeling it with a more simpler shape like a sphere is a way of like utilizing or I guess experimenting with this. So yeah. Okay, so that's how you experiment with wrap cosine in about 5 minutes. That's the idea there. All right. So we could generalize that model by saying how much of it, and then your artist can say, well, I need this much out of it. All right. But there's obviously more to it. You can't just say wrap cosine and that's it. There's more to the technique, but that's the basis behind it is by adding, 1/2 times 1/2 to dot product. Okay, fun. Let's go ahead and talk about per sample operations. Okay, so this is a more or less the one pipeline. Okay, so vertex specification or the data goes in the vertex shader. Then we do the post processing for the vertex. That's only if you're doing tessellation and geometry shaders. Then you do primitive assembly. So you're basically going to turn it into, prepare it for rasterization. Then we turn the resulting triangles into pixels. We run it through our fragment shader and we do our per sample or per fragment operations. Okay. And so there's 6 particular tests or operations that we do: the scissor, the stencil, the depth. Alpha test is not really used anymore in favor of the discard function in the shader. But blending kind of goes along with that. So what do you do when you have parts of the object that are transparent? And then we have logical operations and right masks. Okay, so the scissor test is a way of controlling rectangles on the screen. So you can use a scissor test to basically say, let's draw everything inside of this rectangle and everything else just gets cut off. So scissor test is just a very simple tool. This is, I can see this being good for GUIs, right? You're trying to maybe render a scene inside of a box, inside of your frame buffer, and you don't want the edges to spill out. So you could use a scissor box to kind of say, don't let anything draw outside this box, okay? As opposed to the viewport. So you may want the viewport, right, to be set up so that the whole screen is drawing something, but then only you might only want to render a portion of that box of the viewport. So this is a way of controlling what part of the viewport is visible. And so the ones that we're discarding, right, are the ones outside the scissor box. Okay, so that's what we call that. This is actually pretty simple. This is going to affect commands which write to the frame buffer. And what that means is that, like I said, if we're drawing outside the box, we don't draw it. But we might be using compute shaders. And so one might ask the question, well, what happens if I'm running a compute shader? And so what we do there is, because they don't write to the frame buffer, then the default behavior is nothing happens to your compute shaders. So you can use this alongside a compute shader and it's going to operate correctly. All right, this one's pretty simple. It just, if it's outside the box, then don't do anything with it. The next one is actually really useful. This is called the stencil test. And the stencil test is going to be done after the fragment shader, but before the depth test. Now, so there's 2 elements with the stencil test. And the first thing is we're going to compare the stencil value against whatever is inside the stencil buffer. A stencil buffer is typically, you can pretty much bank on having 8 bits for a stencil buffer. So it's an integer-based value, and it normally sits alongside the depth buffer. So a very common format is 24 bits for depth, 8 bits for stencil. Another common format is 8 bits for stencil and 32 bits or floating point number for depth, all right? And you can use stencils for shadows and for reflection, okay? So here's one, how it basically works. So you're gonna write a value into the stencil buffer. There's a test first. So we might use, the function is, we'll never put that stencil value in there, always put this value in there. So you're trying to replace the value. Only replace the stencil buffer value if it's less than or greater than, equal, so on, okay? So then the second part then is what value is going to be used, or what operation is going to be used for affecting the stencil value. So one is keep, which means no matter what I'm actually trying to do, keep the value in the stencil buffer. The other one is 0, so put 0 in the stencil buffer. Increment, just add 1 to whatever's inside the stencil buffer. Decrement, decrease that number by 1. Invert, I assume that just means 1 minus whatever's in there, so 255 minus whatever's inside of there. Replace, just stick whatever I'm about to put inside the stencil buffer. Increment wrap means that if I'm counting up, 192 or 240, 250, 255, then go back all the way down to 0. So wrap around. Same thing for decrement wrap. And then if that, if that test fails, then we're going to discard the fragment. So here's how we can use it for stencil shadows. All right. So the main idea here is that we can calculate we can calculate more or less, are we inside of a volume created by the shadow? So if you can imagine a light, right? You have a flashlight and you hold up your fingers on the wall, you shine the flashlight on your hand, you can imagine that there's a volume of air essentially behind your hand that's everything in there is in shadow. Okay? So the idea behind stencil shadows is when we go into the stencil shadow, we'll add 1. And when we leave a stencil volume or the shadow volume, then we'll decrease that number by 1. So basically, if we're that number, then when we're drawing, if we're inside the stencil, or if we're inside the a shadow, an area that's in shadow, then that number will be positive. And if we're not in shadow, then that number will be negative. I mean, not negative, but 0. Okay, so we can use stencil shadow. So that's what's going on over here. So we can calculate the stencil volumes from this geometry. So it's something you have to calculate, and that's why it's kind of a pain in the butt to do. But the idea here is that as you can't see it. There we go. So the idea here basically is as we go, so this is in shadow. So clearly this light, if we were to project the geometry onto the plane here, we can see that this area is in shadow. So we're going in and we go out. And so you can see those areas where it goes in or out. So that's one way of doing a stencil, all right? Another way, a cheap way of doing it, is to just flat project the geometry on the ground and then mark the stencil wherever that geometry is drawn. So if you know you're going to be doing a flat plane, then you could actually just project your geometry according to the direction of the light source so that it goes on the plane. And you can just mark the stencil. You could just say, okay, yep, this area is in shadow. And then when you draw your scene, you'll draw it 2 times. You'll draw one scene with the shadow on. And so only the samples where it's positive gets that one. And then you draw it again with it lit. And if the stencil buffer is set on, then you don't draw the shadow in that area, or the lit surface in that area, okay? And then another way to do it is the stencil reflection. So this is kind of interesting. So the idea here is that you would take the ground plane and you would say set the stencil to 1 if we're drawing the ground plane. And then what you would do is you would take your geometry and you'd mirror it, so you're drawing it backwards, and then you only draw this object wherever the stencil is 1, and that basically eliminates, anytime you're lifting the plane, you don't suddenly see the dinosaur underneath the plane. Okay, so that's how you do that.
Be correct to think of the stencil shadows as the light source being another camera that's rendering from its perspective, and then whatever it can, the geometry, the primary geometry that it sees is lit, and the secondary geometry is cast shadow.
That's basically what's happening. But what you do is you take the geometry that you want to cast the shadow, and you project it from the point of view of the light source, and you generate a column, if you will. So in this case, it'd be dinosaur shaped. This dinosaur shaped column, and you render that onto the screen. And basically, as you're going in and out of the stencil volume, because you count when you're going in and you count when you're going out, then that's when you get the areas that that are going to be shadowed. Now, if you have some problems though, because what if you're inside the stencil volume? Well, clearly, as you're drawing it, you only get the ones as you're going out versus, the ones that are going in. So there are some nuances that you have to do there. But the stencil test is pretty popular.
If you were inside a shadow, everything that it would just be opposite.
Yeah, so there are some techniques. One's called Carmack's reverse, which was kind of made popular with Doom 3. So that Doom 3 was always kind of famous for its hard edge shadows, but that's because it used stencil shadows. So that's one technique there. The depth test is another very important one. And that's because, and we've kind of seen the transformation, how you get the Z value, right? Because we have the projection matrix or the perspective matrix, and that's going to map our Z values from, it depends if you're using DirectX or OpenGL, but you'll get values ranging from 0 to -1 or values from 0 to 1. And it just depends on whether you are perceiving the Z axis is going in the screen or out of the screen. Okay, so OpenGL uses a right-hand rule, which means you got X, Y, Z. So positive Z is coming out of the screen. So then you're always drawing negative Z values. So you have to map those to positive values because you're using an unsigned integer to represent depth. Okay, so then what you can do, the default value is just less. And so when you write a new fragment to the, or you're preparing to write a fragment to the color buffer, you check your depth value. And if it's less than the one that's already in there, then you draw it. And if it's not, then you just throw it away. So what you do at the beginning of the renderings, when you're going to render your screen, you clear everything out so it's the far value. And so now every time you write into the depth buffer, whatever's closer will be drawn over whatever's in there. And it's pretty quick to do a clear on a depth buffer. So they definitely have efficient ways of doing that. But the two techniques that use the depth buffer are, one's called early depth test. So if you know that you're going to have some expensive shader trying to do drawing, it would definitely help to figure out if you can throw that fragment away before you even get there. So one method is to do an early depth test where you can do a pre-pass. So in other words, you just render depth first, and then you render it again. So like the G buffer is an example of doing this. You render it again, and only the samples that are going to be drawn with the fragment shader will get done. Now, the way that your rasterizer is rendering is sometimes you'll be rendering one rectangle at a time. And so it can actually sort all those samples as they're being drawn and decide in advance, because you're using like hundreds of cores, right? Figuring out all these, you can figure out in advance which ones are going to, if you have that condition already. So you can easily calculate the depth values and then quickly in that lump, in that grid there, know which ones are going to be tossed out before you start evaluating them. So their early depth test basically is our way of doing that. And then there's shadow mapping, which we'll go into more detail in a future lecture. But the idea here is that you would render the scene from the point of view of the light source and render that into a depth map. So now you know approximately from the point of view of the light, how close are all the objects to the light source. And then when you render your scene from the point of view of the camera, then you evaluate what would the depth be according to the light map, because you'll be seeing things that the light map could not, or the shadow map could not have seen. And then you check, is this at least as close or to light? Then you know that that's not in shadow. And if it's further away than the sample that the light source calculated, then you know that element's in shadow, so you can shade accordingly. And shadow mapping is probably, it's one of the easiest things to do because it's all image space. And you don't have to do projection geometry on other geometry. You don't have to do any of those geometric solutions. So this is normally the preferred way of doing it. And there's a lot of different variations on this technique. Okay, so that's the depth test. So we typically use it for, sorting which objects are closer, but we also use it for shadow mapping, so shadows. Okay, then we have alpha test or blending. So the idea behind the alpha test is that if you if your alpha basically didn't meet a requirement, like you would say, we're going to throw away all the alphas that are 0. So maybe you have a texture map of a picket fence, right? And you can just set the alpha value to 0s for those areas. Then you can just say, well, don't even draw this pixel because it's transparent. So this isn't used as much anymore because you can use discard in your shader. So as you read the texture map, you just check the alpha value and you say, okay, throw it out. Okay. So as an example, inside here, what we could do, let's see here, let's move some of this calculation out of here so we can just experiment with this. So we'll still return n.l, but let's check to see if n.l is greater than, say, 0.1 and n.l is less than 0.5, discard. So in this case, we should discard a certain portion of the, well, assuming we didn't, okay, that's fine. Yeah, it'll just copy it to X, Y, and Z. Let's refresh that. All right. Maybe you didn't like that. Okay. Let's just throw out the samples. Maybe we discarded everything. Okay. Let's only do that over here. If color.r is less than 0.1, discard. Let's just discard colors at the red component. Okay, so we should be tossing away. Yeah, there you go. So we can just use the discard to just toss away values that are not very lit. Okay, so there you go. There's some, look, we tossed away the bottom of the box. Okay, so if we were to change the sun elevation, we basically can control what gets drawn or not. So discard can be a very powerful tool. Okay, so very useful too if you're doing transparent textures. Okay, and then we have alpha blending, which is we're going to apply a function to the source and destination colors. So this is the formula that's used. So we have a factor, this S, for the source color and a factor for the destination color, and then we just add them together. So the two approaches for this is like additive blending. So we can just say 1 and 1. In other words, just add the source plus the destination. Okay. And then you can also use 0. So maybe you don't want the destination, but you do want to apply your this blending factor to the source color or to the destination. So there's different things you can apply. Subtractive blending is this is a very popular one, is source alpha and 1 minus source alpha. So over here we say, okay, if this is 1, then this will be 0. If this is 0.5, then this will be 0.5. If this is 0.25, this will be 0.75. And so you can adjust, like in this image over here, you can adjust whether this green ball is, how much of it is masking the red ball. But this is going to require sorting because you have to know if you draw one object first and then the other, it might not work because technically you've already you've eliminated the ability to actually render do blending because of the way that it's been drawn. So typically when we're trying to draw, we would prefer that we're drawing from front to back because we want the Z values to be as high as possible or as close as possible. And for blending, we actually want to draw from back to front because we want whatever objects in the front to go ahead and color the objects behind it. All right. And it's very difficult to do it the other way around, where I say I draw the red sphere in front, and now I'm trying to blend the green one in behind it. It kind of doesn't make sense to do it that way. So transparency or translucency, this is how you do it. And we can take a look at, we'll look at this more when we're talking about texturing, because some of the power in this is just having the ability to like load in textures that have all the data we want to vary over the surface. Okay. Logical operation. Originally, I just wrote nope on this slide. This hardly ever gets used. It allows you to apply a bitwise operation to the frame buffer. So I've never used it. You probably never use it either. And then right mask is useful for debugging. I like to use it to debug shadows because I'll render a color buffer from the viewpoint of the light, and I'll render a depth buffer. But since you can't just draw a depth buffer to the screen, I can take a look at the color buffer and then just know, yeah, I've got the view matrix set up correctly. All right. So anyways, that's all I had for today. So we were talking about the presentation, the video for Monday. And next week on Monday will be the state-of-the-art presentation, and I'll send out an announcement to remind you. And we'll have the tests will be graded before Monday. So, but you guys know what answers I was expecting, so you probably gauge approximately where you are or what you need to work on. Okay, that is it. So thank you very much for your attention and a good class discussion.